In this lecture, we're going to cover several types of crystalline solids. So there are a number of types of crystalline solids. We've looked at the structure, so now we're going to discuss what subsets there are. And we usually classify them depending on the type of particle that composes the solid. So we could have a molecular solid like ice made up of water molecules. We could have an ionic solid like sodium chloride made up of sodium and chloride ions, or an atomic solid made up of single atoms. So diamond is a good example, or graphite. So this flow chart goes through the different types of crystalline solids and their properties. And so we're going to go through each of these. We'll talk about molecular and ionic solids, and then the three subsets of atomic solids in a little bit more detail. So you may want to pause, sketch this out, and try and fill it out as we go through so that you can kind of think about ways that you might organize this information for yourself. So how are you going to think about the components of these unit cells, the forces that hold them together, or how they relate to each other via melting point? So I'm going to start with molecular solids. These unit cells are occupied by molecules, and the covalent bonds hold the individual atoms within the molecules together, like the covalent bonds between the hydrogen and oxygen atoms forming a single water molecule. However, the two water molecules are held together by intermolecular forces. So these we talked about previously. These are the dispersion forces, dipole-dipole interactions, hydrogen bonds, those sorts of things. And if we look here, we see that we have these two molecules, and carbon dioxide compared to water, they are both small. Carbon dioxide is actually a little bit heavier. It has a higher molecular weight. Yet the melting point of carbon dioxide is minus 78.5, so pretty close to minus 80 degrees Celsius, whereas the melting point of water is 0, or ice is 0. And so the reason for this is the type of intermolecular force that holds these together. So the intermolecular forces that hold water molecules in their crystalline structure in a cube of ice is hydrogen bonds, which are much stronger than the dispersion forces that hold together nonpolar carbon dioxide molecules. Something else I'd like to point out here is the distance between water atoms and water molecules, and carbon dioxide molecules. So here we see a lot of empty space. This here is why ice is so much less dense than water. That large amounts of space between the molecules here allows the solid water to be more spread out and less dense than liquid water. Next, we will talk about ionic solids. So here we have a unit cell that is occupied by ions. These are held together by Coulombic forces, or what we might call an ionic bond. And because these forces are much, much stronger than intermolecular forces, ionic solids tend to have a much higher melting point than a molecular solid. So for example, sodium chloride has a melting point of 801 degrees, while carbon disulfide, which as a molecular solid with a higher molar mass, melts at minus 110 degrees Celsius. So we'll be looking a little bit more in more detail at ionic solids later. But for now, just know that they are held together by their positive and negative charges, and that net charge would be 0 for the unit. I want to talk briefly about this lattice energy because we want to remember where this energy comes from. So we calculate the lattice energy of a crystalline solid by shooting gaseous sodium ions and chloride ions, for example, at each other, and then they coalesce and form a structure. And there's an amount of heat released, and that heat that is emitted is what is measured. So this is an energetically favorable reaction. So that energy is emitted as heat, and that comes from the Coulombic attraction between the positive and the negative ions. The lattice energy of ions is affected by packing. The closer the packing in the lattice, the greater the lattice energy. And because these ionic compounds they have to contain both types of ions, cations and anions, the coordination number of the unit cell represents the number of close cation-anion interactions. So because those interactions lower the potential energy, the crystal structure of ionic compounds is the structure that maximizes the coordination number while still accommodating charge neutrality, because each unit cell has to have a neutral charge. So in general, the more similar the radii, the higher the coordination number. So cesium chloride is a really good example of an ionic compound with cations and anions of similar size. The cesium radius is about 167 picometers, while chloride is 181. So in the cesium chloride structure, the chloride ions are occupying the lattice sites of a simple cubic cell, and there's one cesium ion in the very center of that cell. So the coordination number for cesium chloride is 8, meaning that each cesium ion is in direct contact with 8 chloride ions. So the cesium chloride unit cell contains one chloride anion and one cesium cation. And it's one chloride anion, remember, because we've got an eighth of an ion at every corner, and there's 8 of those, so 8 times an eighth, and then 1. So that gives us a charge of -1 and +1. Sodium chloride shows us very different sized ions and how they pack together. With sodium's radius is 97 picometers, and it's much smaller than chloride's 181 picometers. So the crystal structure has to accommodate the disproportionate size of these two ions. So theoretically, the larger chloride ion could fit as many of the smaller sodium cations around it as possible, but remember, we have to keep the charge neutral. So we have to have a charge of +1 and -1 per unit cell. So the structure that minimizes the energy has a coordination number of 6. And so we see this, the rock salt structure. It's that nice square cubed lattice. So the greater the disproportion between the sizes of cations and anions, you get to the point where you can't even have 6 as your coordination number. And that could give you a coordination number of 4, which is what gives you that tetrahedral whole. So you'll end up with a tetrahedron with one atom in the middle. And a good example of that would be something like zinc sulfide, where zinc has a radius of 74 and sulfide has a radius of 184. For atomic solids, we've got 3 different subsets. So for non-bonding atomic solids, these are held together by relatively weak dispersion forces. So we have to maximize these interactions, and that allows these to form these very closest packed structures. So this would be like a face-centered cubic structure. However, despite this close packing, they have low melting points because this is simply dispersion forces at play. These are cells entirely occupied by noble gases. They're all gases at room temperature, so we know they have a very low melting point. And these are non-bonding atomic because noble gases exist just as single atoms, and they don't form bonds. For metallic solids, these are held together by what we call a metallic bond, which is basically metal cations surrounded by a sea of electrons. So like a bunch of marbles with peanut butter smeared on them would be a way to visualize this. And they're not directional, so they can pack together just like a bunch of marbles might. And so they will crystallize in the closest packed structure they can. Now, metallic bonds have varying strengths. We've got metals that are a liquid at room temperature, like mercury, or a near liquid at room temperature, like gallium. And some metals have a really high, really high melting points, things like gold or iron. So what happens is that it depends on how these pack together. That will tell you what kind of, that will give you an idea of the behavior of the compound. So the last atomic solid is the covalent network solid. The bonds between these particles are covalent, which leads to very rigid structures with high melting points. So you can see here, this is kind of like that tetrahedral hole. It's not exactly, but it kind of looks like that. So these bonds between, for example, silicon and oxygen, these are, this forms glass. It's a very rigid structure with a high melting point, and the unit cell is occupied entirely by non-metal atoms. So we call this a network covalent atomic solid because these are restricted. The shapes of these are restricted by the covalent bonds themselves. So they don't form very close packed structures because these are rigid bonds that are holding everything in place. So you could kind of think of this if you've ever played with Tinker toys, where you have the long sticks and then you have the small wooden pieces that you attach to the ends. So these are more like that, where you have a long rigid bond like that stick, and then you have the wooden ball or bead that goes onto the ends of those. So you get this rigid structure that's very regular in shape, or you get the rigid structure that's not very regular in shape, which would be an amorphous solid. These are really important in industry, and we will not be discussing them in great detail. However, if you are interested in learning more about them, feel free to read section 12.6 of the textbook. Okay, so now hopefully you were able to fill out some of this table. If you haven't yet and would like to go back and review those, please do. Otherwise, I'm going to go forward and we will talk about, we'll summarize what we've just discussed in this table here. So the component of the unit cell is probably going to be the easiest column to fill out. The crystalline molecular solids, they have molecules that make up the components of the unit cell. And the forces are all of those IMFs. So it could be dispersion forces, dipole-dipole interactions, hydrogen bonds, something like that. You will not see ion dipole in the molecular crystalline solids, because they would involve an ion and a molecule, and we're talking about solids where that doesn't really happen. The melting point of these compounds is relatively low. That doesn't necessarily mean that it is going to be a solid only like at very cold temperatures, but it's very low compared to our ionic crystalline solids, composed of ions, and the forces are those Coulombic attractions. So oppositely charged positive and negative ions are attracted to each other, and that allows for a very high melting point. It is a lot of energy involved in separating a full negative and a full positive charge. Our atomic non-bonding crystalline solids are noble gas atoms. These are held together primarily by dispersion forces because they are single atoms that are nonpolar, that have no dipoles, no charges, and so they consequently have a very low melting point. They're all gases at room temperature. Our atomic metallic crystalline solids, made up of only metal atoms, they have that metallic bond. So it's that charged cation and surrounded by a sea of electrons, and they have that variable melting point depending on their structure. Finally, we have our atomic network covalent non-metal atoms like carbon, silicon. These are covalent bonds, and they have also have a very high melting point. So let's do a couple of practice problems to try and solidify our information about what, or try and practice what we've just learned and try and solidify what we know. Solidify. So let's classify each solid and place them in order from increasing melting point. So here we have magnesium oxide. It's a solid. We have ethanol, solid ethanol, and solid krypton. So first off, we need to think, what types of molecule is this? So this is actually a metal and a nonmetal. So it must be an ionic solid. We have methanol or ethanol here, and we have, so what we have are a molecule that is then probably interacting with other ethanol molecules via intermolecular forces. So this is most likely to be a molecular solid. Finally, we have krypton all by itself. It is a noble gas, which tells us that it is an atomic non-bonding solid. So we know of these three that the atomic non-bonding solid is likely to have the lowest melting point. And we know this from experience because noble gas at room temperature, and ethanol is a liquid at room temperature. So krypton probably has our lowest melting point, followed by ethanol, and lastly, the ionic compound of magnesium oxide. Last, we have a layer of sodium atoms, and we're looking at it from a side view. So let's complete the layers and show simple qubit packing of a sodium cube. So this is what we would do. We would just pack them all right on top of each other and form a simple cube. So what kind of solid is this? Well, if it's a simple cube, it has to be the basic cubic solid, which is simple cubic. It is a simple cubic structure because it is simple cubic packing. If you would like to read more about this, you may. However, you will only be tested on the content covered in these two lectures and the lab activity.